Called the rational root theorem, what we're going to look at today, but the topic, finding rational roots. We're going to try to determine any rational roots of polynomial functions, and then we're going to look at any irrational imaginary roots as a result of that. So before we start this lesson, you have to go back. What does rational mean? What does rational mean? As opposed to irrational, obviously. James?
Real.
Irrational and rational are both subsets of the real numbers. So rational numbers are a type of real numbers, but they don't mean they're real. What does it mean to be rational? Say again? Yeah, if the decimal is terminating, so like 3.5, or terminating, not just terminating, what else could it be? Put into a fraction, and decimally, like 1/3, it's not terminating, right? 1/3. What is that as a decimal? 0.3 repeating. So remember we talked about rational numbers are either, you can have some sort of a pattern that you can like notice, identify, 2468, 2468, 2468, like over and over again. So you can make a repeating decimal. You can have a terminating decimal, but both repeating decimals and terminating decimals end or turn into fractions when you look at them. As opposed to numbers that are irrational, right? Irrational numbers have no pattern to their decimals. You can't pick up on a pattern. There is no repeated pattern over time. Traditional examples we always give because they're very simple, and there are many of them. Square roots of any numbers that are not perfect squares. So radical 2, radical 3, radical 5, radical 6, 7, 8, 10. We're skipping the perfect squares, right? So those are irrational numbers. Or the other type, which James was kind of alluding to real and imaginary, are imaginary roots. So we're going to use this theorem today, and it's going to allow us to look for rational roots. Rational roots. All the possible rational roots. So let's take a look at this first. So take a look at the setup of this function here. First, it looks like a lot of gibberish. You see a sub n, x to the n, a sub n minus 1, x to the n minus 1. It looks like a lot of fancy stuff, but it's not. Imagine n was 3, right? This would mean, okay, so f of x is going to be some number times x to the third plus some other number times x to the second plus all the way down to 0. That's all that's saying. Where I put the number symbol, that's a sub n. Those are just coefficients. A, B, C, D. Okay, so a sub n is a coefficient. Those are numbers. N is 3 in this case, as I said. Let's make it cubic. If this is 3, the next one is n minus 1. Makes that 2. The next one will be n minus 2, which goes down. So what we're saying is for any polynomial function, if we can look at what's called p over q, where p is any factor of a0. Well, what's a0? Look at the original function at the top. What is a0 going to be for all of our polynomials if it's that last term there? What do we call that? At the end. Not the remainder. Close though. I like the idea it's at the very end there. But if I have like a plus 7 at the end, it's the what? What's the term for that one? It's a number by itself, no variable. What do you call it? What's your vocab? Chapter 1, earlier in the year. A number by itself is called a... There it is. The sneeze is going to come to you. Great. A constant. So the factors of the constant a0 divided by the actual factors of the leading coefficient an, whatever this number is. So for example, if we had y equals 2x to the fourth plus 5x squared minus 3x plus 10. The goal is to look for what's called p over q. And again, p is the factors of this. Q is all possible factors of this. That's all that's saying up top, just in another way. Okay, your book states it this way. I want you guys to be starting to get familiar with notation. A sub n, that just means some coefficient. A sub n minus 1, the next coefficient over and over. So what you're doing is you're looking at the constant over the leading coefficient. And again, you're looking at the factors of those. What are the factors of 10? Simple, quick, simple. What are the factors of 10? Inigo, factors of 10?
1,
Yeah. And what do we recognize? They could be what? To get 10, can't I do -1 times -10 also? So we have to put plus or minus out in front. Okay? Then we go over to Q. Q is listed as 2. Again, this is P, and this is Q. So then we list the factors of this. Factors of 2 are just 1 and 2. Obviously, again, plus or minus. Now, if you don't list plus or minus here, that's fine, as long as you list it when you write your P's over Q's. And here's what I mean by P's over Q's. How many combinations do you have of P's over Q's? I could do 10 over 2. I could do 10 over 1. Some people start with the highest, some start, it doesn't matter, honestly. Okay? I could then do 5 over 2. That's P over Q. Or 5 over 1. Again, we're looking at all the possible values of P over Q. So we have 5 over 2. Should I write 5 over 1? Why don't I need to write 5 over 1? Same as writing 5, or what else that's already in the list? 10 over 2 is already there. So later we're going to do something, we're just going to reduce our list. And we're going to do this. We're going to write it like this afterwards. See how I'm simplifying everything? So there's no need to write 5 over 1 again. But again, you're looking at every possibility of P. P could be any of these 4 numbers up here over any possibility of Q. So we did 10 over 2 and 10 over 1. We did 5 over 2 and 5 over 1. Then we have to do 2 over 2. And then 2 over 1, right? There's 2 over 2 and then 2 over 1. Both of which can be reduced to 1 and 2 now. See how I'm reducing them as I go along? Sometimes it helps to not repeat them. It doesn't matter, obviously, but it's extra work. And then the last combination could be 1 over 2 or 1 over 1. 1 over 2 is important to write, but I do not need to write 1 over 1. Why don't I need to write 1 over 1? Alex, why don't I have to write 1 over 1? Yeah, where is it? 2 over 2 right here. Okay, 2 over 2 is already written, which becomes 1. So writing 1 over 1 would become redundant. All right, so our values that roots could be are right here. Those are all the possible values. So go to your synthetic table. And in your synthetic table, what you would do is you would try these possibilities of numbers out here, and you would try all of these values. Now, for the section 8.7, what I'm going to have you do to make it easy first, to make it easy on you, is I'm going to allow you to look at your graphing calculator and look to see where the x-intercepts are, approximately where they are. Okay? And that will help you to choose certain values you want to try. Now, once we do 8.7 now, I'm going to let you do that to make it easy, okay, ease you into it. We're going to do an extra section that I was telling you about that's not in your book that has you do it without a calculator. And you can use all these rules of like whether these numbers are positive or negative or alternating to indicate where you should search. Okay, it'll help you to limit your search domain. For now, though, what I want you to do is go back up to the original function we had. And let's take a look at the graph of this. So go ahead and graph this in your graphing calculator. Go to Y1, please. I'm going to pause and graph it on the iPad so you can see. Alright, so let's move on to the next one. But as you saw, again, no real roots in this graph because the graph and no x-intercepts. So there are 4 roots. They are all imaginary. They come in pairs of 2. 2 imaginary roots and then another 2 imaginary roots. Let's go look at examples where we can find ones that do work. Take a look at this one. I want you to verify that the roots of the following equation satisfy the rational root theorem. Well, look, I factored it for you on purpose. So what are the roots? Right away, what are the roots? It's already factored. Tell me the 3 roots of this one. What have you got, James? The 3 roots for this.
4.
Yeah.
2 over 3.
Positive, but again.
And 5 over 4.
And negative. Be careful. Remember, they're always equal to 0, right? So you'd have to move the 5. You'd have to move the 2. So we've got 2/3. We've got negative 5/4, and 4 is our roots. Well, do those satisfy the rational root theorem? Go ahead and list. What's P over Q? Here's P right here, 40. Here's Q right here, 20. Factors of 40. 1, 2, 4, 5, 8, 10, 20, 40. Look at all of them. And then the factors of 12. A lot again. 1, 2, 3, 4, 6, 12. Can you somehow get 4 2/3 and negative 5/4 out of all those? The easiest one obviously is 4. 4 comes from where? Several ways you can get 4 here. James?
4/1.
4/1 works. Where else could you get a 4? Where else could you get a 4? Chandler?
8/2.
8/2 for sure. That works also. Can we get 4 anywhere else? I don't think so, right? 20/5, 4/... No, that's it. All right, next. Can I get 2/3, please? 2/3. Where do I get 2/3 from? Right here and right here. Again, obvious, 2/3, right? 2/3. And then the last one, 5/4. 5/4. Again, remember, my answers are always plus or minus for all of my factors, because when I factor, I can get the positive or the negative factors for each. But all of those 3 answers do appear in my list. Wouldn't this be a really long list to look through? You'd have a ton of values because of all the values of P, all these factors, all the values of Q, all of these factors. Okay? So all we did here for this one is verify the rational root theorem. So let's look at a general approach of this. I wrote you a few. First, list the possible rational roots, P's over Q's. Okay, you don't have to write this obviously, it's on the next slide. Second, use a graphic calculator to determine which of the possible roots may in fact be roots. So if you have like 10 possible answers, you can quickly look near the x-intercepts and see which one you want to actually test. You're not going to use this, you can use the zero function on the calculator to actually get the exact value if you want, but I want you to show mathematically. Look at part 3. Use synthetic division, synthetic substitution, which we know it as, right? But it's really division, to show that the number is indeed a root, and eventually reduce the equation down to a second-degree polynomial, and we called that the other day the depressed equation. So we could simplify that. And then finally, when you get to the quadratic, or second-degree polynomials, or quadratic, use the quadratic formula or factor to determine the other 2 roots. They may be imaginary, they may be irrational. It could be rational, I guess. But yeah, they definitely could also. So let's look at an example. So let's start with our P's over Q's. List all the possible factors of 10, and then all the possible factors of 6. And go through all of your possible factors when you look at P over Q. You should be able to do this faster than me. All right, you got a head start. 1, 2, 5, 10. 1, 2. Oops, use blue. Just keep it consistent. 1, 2, 3, and 6. Remember, it's plus or minus for all of these. So our possible list starts here, plus or minus. We start writing it. How do you want to do it? It doesn't matter. You could start with all the 4 from the top, from the P's, and then all the Q's, or the other way. I'm going to start this way and do 1/1 first. And then I'm going to do 1/2. And then 1/3. And then 1/6. That's my first 4. So once I've done that, I can kind of cross off the 1 at the top. A lot of people just make mistakes with the work here. Please be careful. If you need to, cross this off. You're done with the 1 on the top now. Then go to the 2. You got 2/1. Now I could write 2/2, but should I? Why not, Alex? Yeah, 2/2 is the same thing as 1/1. So it's not worth writing 2/2. I could write 2/3 though, that's worth it. And then should I write 2/6? Why not, Morgan? Yeah, 1/3 is already listed right here. So by listing 2/6 is the same thing. So I'm done with the 2 now. Then I go to the 5. 5/1, 5/2, 5/3, 5/6, and then last but not least, 10/1. I'm not going to list 10/2 because I already have 5/1. 10/3, and I'm not going to list 10/6 because 10/6 just gives me 5/3, which I already have. So these are all my possible rational roots. Now, there's a lot of them. They're positive, they're negative, there's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2. 24 possible roots. So, the next lesson, we're going to see where you can test anything. And I'll show you which way you should guess next based on the signs. For now, I want you to just practice. So go to I1, type in the original function at the top, See where the x-intercept is closest to one of these roots, please. If you take a look at this graph here, it's tough for you guys to see it now, I apologize. But what we're going to see here is that we have three locations where there are possible roots. We're going to see that we have one of these roots and follow the line. One of these roots is right here. One of these could be right here and one right here. What's the one that's the most obvious by looking at this? That's definitely on the list, James. 2. Right here is on the list, and it's absolutely one of the roots. Now, on your graphing calculator, it might not be as obvious, so maybe you need to zoom in. Look at my window right now. If I were typing my window on the graphing calculator, my window is showing on the x-axis from -1 as an x-min and +3 as an x-max. So maybe go to your window and change it real quick so you can see this a little bit better. Hit window at the top, make the x-min -1, make the x-max +3, and then hit graph. You can change the y, but the y doesn't matter. All that matters is the x, really. And hopefully you'll be able to see a little bit better that at x equals 2, it looks like it crosses perfectly. Now, maybe it doesn't. Maybe it's like some irrational root that's 2.01 something. But it's probably not. There's a good chance that these are probably either irrational, or these actually might be like, this might be -1/3. It looks close to -1/3, doesn't it? So I could even try -1/3. This over here looks like 2.5. Maybe it's 2.5. Maybe it's 2 1/3. I don't know. Okay, we got to see what we have. So what I would test is 2 though. Because if I test 2 in the original function, let's write the original function out. What's going to happen if I run a 2 through here? Again, my original function, I'll put a line underneath so you can get... There's your original function right here. Okay, boxed in there. So we're going to use our synthetic table here. We're going to use synthetic division here, to go through this table to see what we get as our answers. Remembering, where do these numbers come from up here? Quickly, where did this come from? Yeah, the coefficients of the original function always go along the top. Can somebody step me through this process real quick again, just to refresh our memory? Will, go ahead.
You bring down the 6.
Always bring down the first number. Always bring it down first. Then?
The 12 minus 25 is -13.
So we multiply these two next, always. Multiply this like you're distributing to give you 12, and then add this number, that gives you a -13. Go ahead, Will.
And then 2 times -13.
Multiply these two to give you -26.
Yeah, and then plus 21 is -5.
And then multiply these two. Go ahead.
And then -5 times 2 is -10 plus 10 is 0.
It's 0, isn't it? And we remember that this is really the y value. If you forgot that on the test, you should write that down again here. This is the x value you plugged in. This is the y value. Remember, this is the same thing as substitution, except for one thing. What one thing is the difference here? That's really important now. If I were to directly substitute a 2 into this function, everybody look please. If I substitute a 2 right here, here, and here in the original function, again I'm referring to this line right here, if I plug in a 2, I will get 0 as an answer, which means that 2 is absolutely one of the roots, and we can see that. Because 0, this is the y value. 2, comma 0 is one of my coordinates. That's what this is telling me. 2, comma 0. So why didn't I just plug the 2 in here and test it? Why did I use a synthetic table? Chandler?
So you could get the second degree polynomial.
Yeah, so you can get this next equation we call the depressed equation or the secondary polynomial. And that comes from, remember, these three numbers. Bring these down. It's really important to recognize that when you get 2 as a root, that means x minus 2 was one of your factors. So you could get the other factor now, which is your depressed equation. Let's write that down. We started with cubic, so this is going to be quadratic now. Remember that this degree right here is always, always, always 1 degree less than the degree you started with. So the fact that 2 is a root means that this original thing already factors into something with x minus 2 involved in it. And then the other quadratic that's left is 6x squared minus 13x minus 5. Okay, remember that if the factor is x minus 2, the root is positive 2. The factor and the root always have these opposite signs. The other factor that's left here is what we bring down. How do I solve that last part here? What would you honestly do? Tell me the truth. James, what would you do? I would probably do the same as James. Because to factor something with 6x squared is messy. It's 2x and 3x, or 6x and 1x. I'd go right to the quadratic. Because I'm not even asking you for the factors. The question was find all the roots. So once you get to this point where it's quadratic, use what I wrote in those steps. If it can't be factored easily, go right to the quadratic formula. Let's see. I think we're actually going to get rational roots in the end, believe it or not, even though we're doing quadratic formula here. What do you get under the radical there? James?
7.
7? So radical 49? James? Radical 49?
Yeah.
Okay. So radical 49 is what we're going to get there, which will give us a 7. So we got 13 plus 7 over 12, which is 20 over 12. Or 13 minus 7, which is 6 over 12. Well, take a look at that. That works out quite nicely, doesn't it? Oh, that shouldn't be, actually. Hold on. No, that can't be right, can it? We should have a negative root. Where did we go wrong, guys?
I got 5 over 3 and 1 half.
You got 5 over 3 and 1 half? Yeah, that's what it would become. Something's wrong, though. Are you sure it's 7? Is that right for sure, James? Did anyone else get 7? That might be the mistake. This is negative, negative, which makes this a positive. I don't think this is a 7 here. Somebody else check. James, careful. Look, see this negative, negative? That makes that a positive. So that can't be a 7. Because this is already 169 when you square it. And then you're going to be adding 24 times 5, which is 120 to 169, which is 289, which makes this 17. Be careful, okay? James, how did I know this? Because remember the graph we looked at didn't have one root that was negative, actually? Think back to the graph we looked at a little while ago. One of those roots was negative, wasn't it? It was on the other side of the y-axis. If one of the roots was negative, we got 2 positive roots. Something must have gone wrong along the way.
I have the square root of 289, which is 17.
Yeah. Okay, so we're going to have that 17. That's all right. We're going to have that 17 there, which makes this now 30 over 12, or negative 4 over 12. Negative 4 over 12 is what we had guessed earlier as negative 1/3. Remember earlier we were taking guesses and we said, oh, it's probably negative 1/3 there. So this is going to be negative 1/3, which is perfectly lined up with our graph. And then the other one is going to end up becoming what? We divide them both by 4. Divide them both by 6 rather. 5 over 2. Let's go back to our graph. Let me pull the graph over. Here's our graph. Take a look. There it is. Okay, here's negative 1/3 as one of my roots. That's the negative 1/3. And 5 over 2 is actually 2.5. That's the one right there. So we got 2.5, negative 1/3. And then this 2 again came from when we tested the synthetic table. We got the root there when we tested it in that table. What time is the period? 10:46 or 47? Let's try one more. Read the question first before you start it. If you know what you're going to do, start right away. But if you don't, let's talk about it before you begin. This is a perfect calculus problem. AP calculus on the exam, actually. And then later you have to do like part B, which would involve a little calculus, actually. But this is exactly like a calculus problem, not kidding. So, tell me, if I'm walking across the room, I have some velocity. When do I have 0 velocity? When do I have zero velocity? If I stop. So when I stop, I'm at rest. This problem says determine when the particle is at rest. So what are you going to do with the velocity? Set it equal to 0. Okay, when you set something equal to 0, you're finding the roots. So right away, you're setting this equal to 0, which means you're going right to the rational root theorem. Whenever you set something equal to 0 and you want to solve and it's a polynomial, you have to go right to the rational root theorem. So we list the possible factors of 35 to start. That's P over Q. 35 is going to be 1, 5, 7, and 35. The Q values are going to be 1, 2, 3, 6 again. We've got lots of values here. Now, before we go further, let me point something out. Read the first part of this. It says, defined on the interval from 0 to 5. So, if I get a possible root like 35 over 1, is that on the interval of 0 to 5? Absolutely not. So when you're making your list, if your fraction doesn't reduce to some number between 0 and 5, you don't have to include that. I'm telling you, your search domain is from 0 to 5 along the x-axis. 0 to 5 is the domain possibilities, the x possibilities. So any of these list numbers that come out to be more than 5 or less than 0, you don't have to include. So we don't need any negatives here. 1 over 1 is between that. 1 over 2 is between 0 and 5. So is 1 over 3, and so is 1 over 6. Those are all fractions. They're between 0 and 1, which is included in the region between 0 and 5. We then go to the 5 next. 5 over 1 works. It's just inside the interval. 5 over 2 works. 5 over 3 works. And then 5 over 6 also works. So we did 1, and we did 2, and we did 5. So all those values are good so far, correct? We're good with all those? We then go to 7. Does 7 over 1 work? No, because it's clearly outside the range of 0 to 5. 7 over 2 works. 7 over 3 works. And 7 over 6 works. And then finally, can we do any of them with the 35? Which one can we do? We can do one of them, I think, right? Can we do... Oh no, 35 over 6 doesn't even work, right? Yeah, so none of them work. They're all over 5. Okay, 35 divided by any of these numbers does not become something between 0 and 5. So we don't have to include any of them. So there's our list. Why didn't I put a negative sign on the a plus or minus sign on the outside? Why didn't I make all my choices positive or negative like earlier? Yeah, the restriction sets from 0 to 5. You can't have negative numbers as your answers. And if it's time, usually time cannot be negative. We don't really associate things with negative time. You always say the experiment started at time equals 0, and you count up from there. You never count negative. Okay, so for time, always really positive. So these are our possibilities. We look at our calculator. Go to your calculator, please, real quick, guys, real quick. I know we're going to run close to the end of time here. Go to your calculator and type in that function, please. Oh, the bell is literally about to ring, isn't it? 46. I suppose it doesn't work. That's good. Try to type this in your calculator. So here's what I want you to do tonight. Listen. Tonight, please. Your homework says 1, 4, 7, 9, 12, 22, I think. If you take a look. Do like the first 3 or 4. Do about half of them, please, tonight. We're going to pick up with this tomorrow. Listen. We're only going to spend half a period finishing this lesson. Then we're going to go right into the next section. So you're going to have to do the homework tomorrow night anyway. So we can't get started tonight, please. We'll get through about half of the homework. It's just come out. You can finish this problem if you want to on your own, but we're definitely going to finish it together tomorrow. After we list the roots, what do we always do after we list the roots? Bless you, James. What do you do after you list the roots? Search for? Yeah, search for another graphic calculator. Or just take a look at the graphic calculator. Get an idea of what the graph looks like real quick. Find intervals in which I should search. Please remember that we're looking at positive values. We're looking from on the interval 0 to 5 seconds. So I don't really care about anything else besides that range I'm showing you, or that location I'm showing you there. The y-axis doesn't even matter what you put. So what do you have when you graph this? Where are the roots between? And remember, go to your window, please, everybody, go to your window. Make x min 0. Do you have your calculator? Can you take it out? You have it? I want you to use your calculator. It's on the test. You do not have it with you? I have mine. I'll give it. Does everyone else have a calculator with them? Please, guys, bring this. You need to practice this stuff. Part of your AP exam, part of your SAT, especially the new SAT they just came out with this year, is calculator accurate. 2/3 of it. Which means you need to get used to using this, right? Let's go around. So everybody go to window, make x min 0, make x max 5. Window is along the top, it's along the very top if you can't find it. Hit window, x min 0, x max 5. Leave y as negative 10 and 10, that's fine, it doesn't even matter. It's no difference. James, what do you got?
I got 0.5. And
Did you actually use the function to find the exact root, or are you saying it's between 0 and 1? You did the actual thing. So James did the command where you press second and then trace. Is it right? Trace? Look at second and then hit trace. It says calculate. One of those options says 0, like the word 0. Hit that option. And then it'll say left bound question mark, which simply means guess a number to the left of where it is. So maybe press 0 and hit enter. And then it will say right bound question mark. Press 1 and hit enter. And what that does is this. It allows the calculator, let me move this up so you can see it. It allows the calculator to search between 0 and 1 by making those your left and right bounds. Now, use the 0 feature a lot. Definitely do it. But I still want you to use the synthetic table once you know that 0.5 is one of your roots, and prove that by getting 0 remainder, and then you can use the depressed equation. Okay, so we have one possible root in here. We don't know where it is. Let's assume for now, just hypothetically. And the other one? And the other one? You okay? Yep. You lost the battery. Chandler?
7/3.
7/3? So between 2 and 3?
Yeah.
Okay, 7/3 between 2 and 3. And I think it was looking like this, correct? It went off the screen at the bottom there. So, for this problem, what we're going to do is we're going to take a look at our list. And I want you guys to notice this. Obviously, you have the 0 command on there, right? I know you can find the exact value. But simply look at your list at the top. Which of these values is between 0 and 1, and which is approximately halfway? Obviously, 1/2 is the only thing that seems to work, but you still have 1/3. 1/6 doesn't seem reasonable. It would be like right over here along the y-axis. And if you look at your graph, you can see that it's not really just along the y-axis. But you do have options, right? That's what I'm trying to get at. So these are your 3 options right here. Let's just circle those or box them in for now. Those are your 3 options for the first root. And for the second root, what values lie between 2 and 3? Which of my rational values could it be? Between 2 and 3, there's many options. 5/2 works for sure, right? That's 2.5. That could be it. 7/3 works. 7/6 doesn't. 7/2 is 3.5. 5/6. Oh, 5/6 could have worked for the one earlier, actually, I guess. But that doesn't seem reasonable. Neither 5/6 or 1/6 looked reasonable on the graph. So after that, everything else you can kind of roll out. All right, we're looking between 2 and 3, so clearly we only have 2 options for that. Those options are 7/3 and then 5/2. So please, by all means, go ahead and calculate the 0 so you know the exact value, but you have to run it through the table. You need to run it through the table because the table is what will get you down to a quadratic depressed equation, which gives you the 2 imaginary roots that are on the graph. How many roots should I have for this function? How many zeros or roots for this function should I have? or solutions to the equation when set equal to 0? 4. Because it's t to the 4th or x to the 4th, whatever the independent variable is. We only see 2 real solutions here. Where are the other 2? They must be, if they're not real, imaginary. The other 2 are imaginary roots, which can only be obtained from synthetic tables. So let's go ahead and make a synthetic table. Do you want to use either 1/2 or 7/3 first? It doesn't matter since we know that they're both answers. All right, great. I'll use 1/2. Let's try that. Our numbers across the top. Our numbers across the top are 6, -41, 105, -113, and 35. Let's bring down the 6, run through our table. We're going to get 6. Half of that's going to give us 3, -41, -38. Half of -38 is -19. 105 will give us 86. Half of 86 will give us 43. 43 and -113 is -70. Half of -70 is -35, and 35 is 0. This value of 0 here, remember, is the y value. X, comma, y. So already we know that one of our roots is going to be 1/2, comma, 0. This is one of our roots. It's a root because the remainder was 0 over here. Now, as a result, I have another depressed equation. But here's the thing. What degree is this new equation going to be? This depressed equation, what will it be? To the 3rd. So I cannot get my other 2 roots yet. So what do I have to do still? What do I still have to do if this is to the 3rd now? Chandler?
Do another round of synthetic substitution.
What are you going to use this time?
0.
There's my equation, right? That's the depressed equation from the above row. That's why you're doing the synthetic table, because you get this depressed equation. What root did we use already? We used 1/2, and it worked, correct? Wasn't there another possible root? 7/3. So let's use 7/3 for this equation now. So let's make a subtable, another table with this new row of coefficients here. 6, -38, 86, and -70. We're going to use these values as one of our like top or head for this new table. Our heading. 6, -38, 86, -70. And we're going to try to run 7/3 through this table. It's going to be really messy. So this is not an ideal situation, but we have to do it to get the next depressed equation. So let's bring down the 6 right away. 7/3 of 6. I'm just going to tell you what they are. 7/3 of 6. Well, you can do 6 over 3. Give us 2. That'll be 14. 14 and -38 is -24. 7. You know how I'm doing thirds, by the way? You make it easier. Actually, let me show this. If you're doing 7/3 times 6, 6 divided by 3 gives you 2. And then just do 2 times 7 to give you 14. 14 and -38 is -24. Then go ahead and take -24 divided by 3 to give you -8. -8 times 7 is -56. -56 and 86 is going to give us 30. And again, same thing. Take 30. Since you're doing 7/3 times 30, take 30 divided by 3 to give you 10. 10 times 7 is 70. 70 minus 70 is 0. So this works as well. So it turns out that yes, your calculator did give you the right solutions when you use the 0 function, but now you've got a quadratic. Look, 6x squared minus 24x plus 30. That's the important part here. The calculator cannot give you that. It is impossible. Okay, the calculator will not give you this. There are some like programs and apps and stuff you can download that gets you to do it, but you're going to have to do this by hand on the test. I'm going to give you a part of the test with a calculator and have you do it by hand. Okay, so once we learn in the next section, not yet. In the next section, you're going to see that you can judge your roots based on those rows we keep talking about. So the fact that these signs right here, see how these signs were all alternating? When signs are alternating, it indicates that that root is called like a lower bound. It means that there's not going to be a number smaller than this that's a possible root. And 7/3, isn't it bigger than 1/2? When the 1/2 is there, and these are alternating, we're going to see this in 8e, that extra section, it means that this is like a lower limit. You don't want to search any lower than this. So you'd automatically search higher. So you try roots higher than 1/2. But we'll get to all those techniques. The final answers we're going to get are what? What do we get for the final answers here? What can I do to solve this?
Well, you plug it into the quadratic, or the...
You could, but this might be an easier way. Actually, you might not be able to factor, so maybe it's not easier. I would factor out a 6 first, if that's sensible. Because look, aren't you doing this really? Just make numbers easier, aren't you? Before you go to the quadratic formula. You don't want to have to work with 30 and 24, right? You know what I mean? 24 squared, that's a mess. I would take out the 6 first. And then I would go through it. I would look to see if I could factor this. Can it be factored? How do you know it can't be factored? How do you know that this cannot be factored? Morgan. It's not the reason, but there's an easier reason. Way before you even look at these numbers. Before looking at these numbers, how do you know it can't be factored? If you could factor, what kind of roots would you have? From those factors, what roots do you get from factors? Are they rational, real, irrational, imaginary? How would you characterize roots you get if you can factor? If I get factors of x plus 3x minus 2, those roots are what kind of numbers? Rational and real, aren't they? Didn't we look at a graph of this? How many x-intercepts were there on the graph? 2. So where are the other x-intercepts? They're not there. So what kind of roots are they? Imaginary. So if this were imaginary roots, it can't be factored. So I take out the 6 simply to make it easier work in the quadratic formula. But you can't factor. That's an easy way to check, to think about it mentally. You already got your rational roots. Again, as Chandler said, you could have just gone right to the quadratic formula. There's nothing wrong with that. But if you're doing this by hand, because when you're taking AP Calc, part of the exam, you're going to have to find roots of rational functions, of polynomial functions, of a lot of different functions. Finding roots is like one of the most important things you have to do, literally. You have to do it for everything in calculus. I'm not kidding. So, being able to do this by hand means take shortcuts along the way. So factoring out that 6 makes the quadratic formula a whole lot easier than doing it when you have to do 24 squared minus 4ac, where it's 6 times 30 times 4. That's a real mess. So this will give me 16 minus 20, which is negative 4. So my roots are going to be 4 plus or minus 2i over 2. Those can be simplified further. Simplifying this, we'll divide the 2 into the 4. Gives us a 2 over here. Divide the 2 into the 2, gives us a 1. 2 plus or minus I. Did others get the same thing? 2 plus or minus I. Okay, so these roots are clearly imaginary because we saw on the graph that we only had 2 real roots. These 2 x-intercepts on your graph were the only thing that told you this. That's why you couldn't factor this for sure. All right, let's take a look at the last example. I want to start with the question, what would you do? What would you do to make life easier before starting this problem? I'm giving you a hint. What would you do to make life easier before you start this problem? For example, do not list P and Q right now. What should you do first? Yes, part of the theorem stated this, and we didn't actually look at this. The theorem stated that your coefficients should be integer values. Clearly 10.5 is not an integer. So as Emily just mentioned, let's double everything, please. Okay, double everything to start. and then start listing your P's and Q's. This makes life pretty easy, doesn't it? When it's only 1 and 2 for A. A lot of the time when you have a polynomial to the third or fourth degree, when you're solving a problem like this, your text and advanced tests will only have like 2x cubed or just x cubed. The reason being is it's really tedious when you have like 50 roots to choose from and you don't have a calculator. It would take forever. So traditionally you're going to notice that there's not going to be many. Like here there's only going to be, there'd be still a lot. Looks like 16 options, right? 4 options across the top or 2 options down here, each of which could be plus or minus. So you have 16 options still with only this many values of P and Q. So we're going to list them all, right? We're going to start with simply easiest ones first. Start with 1 over 1, and these are all plus or minus. Start with 1 over 1, and then 1 over 2. 3 over 1, 3 over 2. 7 over 1, 7 over 2. And if anything repeats itself, you don't repeat it, but here it does not. 21 over 1, and 21 over 2. All right, so clearly there are 8 options, but since there's plus or minus, there are actually 16 options here. So we go ahead and quickly take a quick look at our calculator. Go ahead and graph this. Please don't use the 0 command. For the sake of this one, don't, okay? Don't use the 0 command on your calculator. What I want you to do is to try to find out where these roots may be, and then which of these numbers here could be that root. That's a general sketch of what the graph looked like. It should be the same as what you have. Yours might go off the bottom of the graph. That's fine. Okay? Make believe my y, I didn't put any numbers on my y-axis for that reason. So if you made your y min and y max like negative 30 and 30, your graph might look like that. But yours, I have a feeling, shows this piece, right? And then it goes off the graph at the bottom. And then it continues on the right. So you're missing this little bottom loop here. And that's not even what's important. What's important is to look at the calculator and see between which integers does a possible rational root lie. Between which integers, and what are those answers? Between where and where? What's the first solution possibility? Between where and where? Alex, what do you think?
Between 2 and 3.
Yeah, somewhere between 2 and 3. Right, somewhere in this region there's a root. Which of these numbers is between 2 and 3 out of our list? Which of the numbers from our list is between 2 and 3? Alex?
7 and 2.
7 over 2? 7 over 2 is 3.5. That's between 3 and 4. None. So, this root must be what? Come on, people. Please make me happy here. This root must be what if it's not in my list of possible rational roots? Irrational. This root is clearly real. It's not imaginary. Remember, imaginary roots don't show up as an x-intercept. This is an x-intercept here, but it is clearly irrational. Please write that down. This has to be irrational because it's not part of the list above. Please help me out with the next part. Which other one is clearly irrational? Which other one? Between which numbers is there going to be another irrational root?
The first one.
Yeah, between -2 and -3. So between -2 and -3. None of these numbers on the top are between -2 and -3, because look, the plus or minus sign would tell you that if they were between 2 and 3, they would be here also. But if they're not here, they're not here either. So this is another irrational root. Finally, the one option, what would you choose? Which of the numbers along the top is somewhere between -1 and -2? Which of the numbers on the top is between those two numbers? -3/2. -3/2. It looks like the only option you have, right? Nothing else is between -1 and -2. All right, so go ahead and test -3/2. For my coefficients, 2, 3, -14, and -21. Again, make math easy on you. When you're multiplying by a fraction, if you want to divide first, that's fine. Bring down the 2. When you multiply -3/2 times 2, think 2 divided by 2 gives you 1. Those cancel. You're left with a -3. -3 and 3 is going to give us a 0. Then we go ahead and multiply. -3/2 times 0, that's 0. 0 minus 14 is -14. -3/2 times -14. -14 divided by 2 is going to give me -7. -7 times -3 is 21. 21 and -21 is 0. So this is clearly one of our roots because the remainder is 0. It's a remainder for r. If that's one of our roots, well now because we started with a cubic, we're now down to a quadratic. Yes?
Should we make them from 0 actually?
No, because remember that was when we actually did synthetic division. We're really using this for synthetic substitution. So this 0 is just kind of like a confirmation that we're correct in our guess. Please do not use the quadratic formula. What should you do to solve this? Remember, we're trying to get the root, so we set it equal to 0. How do I solve this? Do not use the quadratic formula. How do I solve this?
Can you factor it out?
No, you could take out a 2. Sure. It works. The 0x doesn't matter, right? Obviously, I put this here, but you can drop it off. So you can factor out a 2, and then obviously solve normally. Okay, solve like any other algebraic equation. X equals plus or minus root 7. This is where you got to remember plus or minus. How do you know that your answer is right? How do you know that your answer is right? What's the square root of 7? You don't know, right? But what's the square root of 4? The square root of 9? So it's between 2 and 3, isn't it? And wasn't that root between 2 and 3 that we couldn't find earlier? If we go back up and look at our graph, we know that root 7 is between 2 and 3. Well, there it is. Okay, there's positive root 7, there's negative root 7. So this lesson has really brought together everything we've been doing all year with quadratics, with root finding methods, now with the rational root theorem, with using your calculator to back up your answer, using the 0 command on your calculator. Okay, there's a lot of stuff that we did all together with one lesson, which was what makes this a little bit difficult. Let me see if I want to start. I think I want to start the next lesson. Because AD follows up with that one. Just load the notes for now while I'm thinking about it. 8E, look for 8E, please.